Canvas, I updated the link to a very nice app. So this is a website where they have great app. If you want, even in fluid or modern physics, it's very nice. And I don't know, I think it's maybe HTML5. I'm not sure how they do it, but here you have it here. It's interesting because you can change the acceleration. So you see here, if you have a negative acceleration and you start with a positive velocity, so they have opposite direction. So same situation when you throw something in the air, acceleration is always negative, it's in free fall. But because you start with a positive velocity, so you see it's going to slow down. You see the velocity decreases in magnitude. At the top, it's going to be 0, and then it's negative, so it's going down or to the left, but in magnitude is increasing again. If you have the graph, position versus time, you get a nice parabola curve down. Okay, you see the slope decreases, get to 0, increases again, but the slope is negative. And you can play with that, right? You always get a parabola or a line, right? You can play and see what you get. If you have a positive acceleration, now you have a curve up. Okay, so this is the case when the acceleration is constant. If the acceleration is not constant, then you have to use calculus, right? So you can play with that. So for us, when we say in free fall, we are not taking in account when it's in your hand, right? We don't look at that. We just look when it's leaving your hand.
So when it falls?
No, so when it's in free fall, it goes up and down, or like this. Okay, so I'm going to go back to that because that's what we did last time. So I'm going to review free fall in a moment. But the other thing I wanted to show you, I was delighted because usually I don't like what Google posts, but for once they post something very nice. And you see, it's a nice parabola. And it's going to introduce the next unit, which is projectile motion. So it's a projectile motion, okay? And of course, the equation of motion will be a parabola. Okay, so it's a nice parabola. You see it's slow down, stop, and speed up. And they give you here the equation for the quadratic equation. That's when I was in school. Nowadays you have the TI and you can find the solutions, right? But I thought it was cool, so I'm going to keep it. Now they have, if you look at Google, they have something about the DNA. Yesterday they had something about the DNA, which I thought it was cool that they get a little bit more into science. I don't know now. What is it at? Okay, so here we stopped here. So these are the two free fall situations we can have. So we neglect air resistance. Acceleration is always negative 10 at all time. So that means you throw something in the air, it's going to slow down, speed up. Or you just drop something. So if you drop something, initial velocity equals 0, and then it's going to speed up. So every second it's going to go further down. So you take the same kinematic equation, the same one, you're going to replace the acceleration by negative 10 all the time, and x by y. Now you can be mad. You don't have to go boom. You can also be mad and do this. And if you do this, the initial velocity is not 0, it's going to be negative if you get mad. Okay, so I wanted to show you another app that I have here. So the famous Galileo experiment, except that he used inclined plane to dilute gravity, but the relationship between time and the position is the same, it's quadratic, right? So if you remove a resistance, regardless of the mass, any object will experience the same acceleration. obviously is not going to be the same force, right? Gravity here is pulling more on this one. We're going to see the weight is the mass times gravity. However, this one has more inertia, laziness, because it has more mass. So at the end, they're going to fall at the same rate and they have the same acceleration. So both graphs are on top of each other. So we already analyzed this graph, right? So acceleration is negative 10, initial velocity is 0, and and it's gonna speed up at down. Initial velocity is 0. Now, if you add air resistance here, so if I add air resistance, so now this one has less mass, so it's gonna reach its terminal speed sooner. So now you see they start the same, but the red one is experiencing air resistance. So very soon the weight will be balanced out by air resistance. So we say the net force is 0. If there is no force, there is no acceleration, so it's going to move at a constant velocity. That's why here you see a straight line. So if you find the slope, you will find the velocity. So when you jump with a parachute, the acceleration is going to decrease, and then you get to terminal velocity, and then you are cruising down. Okay, just to make sure. Oh, I lost my app. That's fine. So we did that last time, right? So we did that, and I think we did that. Okay, and so this one, I think we did it, right? So 20 meter per second, it's tossing situation. After 1 second is 10 meter. After 1 second, minus 10 is 0. Minus 10 is minus 10. Minus 10 is minus 20. They are very symmetric with each other. It's going up and then down. So in green, you have the position versus time. So again, it's a parabola curved down. That means the coefficient in front of the t square is negative. If it's positive, it's curving up. And then here you have the velocity as a function of time. So you have to look blue at the blue here. So first it's 20 and then 10 and then it goes 0 because it stops. And then the velocity increases again. So first it's positive because it's going up, stop, and then it's negative because it's going down and it's accelerating. Okay? Okay, so here another slide for you. You see, you analyze the. So someone showed me something interesting that you did in the lab, right? It was very impressive. You got very nice data for the lab, but you have two phases in this lab. You have the phases when the ball is in your hand and you get to the right speed, and then you have the phase where it's in free fall, and then you have the phase when you stop it. You have to stop it. We are only focusing on the phase when it's already leaving your hand, is in the air, and then it's touching your hand. Because to get to the right velocity, you need to have acceleration, and then your acceleration decreases. It's like you're stopping here, and then it stops, right? So the lab that you did was very nice. So anyway, so that's what you will get here. Okay. Okay, so we can do this one very quickly. So typical question here. So you can use that if you want to do a demo. I don't know, you go up a palm tree and you drop a coconut, and then you time how long does it take for the coconut to reach the ground, and you will know the height of the palm tree. I didn't tell you that, okay? I don't want to, that doesn't sound very safe. Coconuts are not safe and palm trees are ugly. I don't think they should be called tree. It's just a stick with a few green stuff. But you can be creative. Okay. Let's do. Come on. Do it. We are looking for the height of the building. So remember, we need always three things, right? Three things that we know. Oh, that's too big. So we know initial velocity equals 0, check. Acceleration minus 10, check. Time elapsed is 3. We want to find the displacement, so delta y. And you know kinematic equation by heart by now, right? So the coefficient is minus 10, but you divide by 2. Okay, so the coefficient in front of t squared is always the acceleration divided by 2. So that will be minus 5t squared. So the displacement is going to be minus 4, minus 3 times 3 is 9. 9 times 5. Very good. So I don't know why it changed to something strange here. Okay, so this is a displacement. It has a vector and a direction. So that's my displacement here. Okay, but I want the height. The height is a scalar. So the height of the building is going to be that. Okay, so you can use free fall to measure the height of a building only if you take something big enough or massive enough that you don't have to worry about the air resistance, right? Okay, so typical question. Okay, another typical question, except they give you part of the solution. You toss something up, it's going to stop and then come back. And they give you part of the solution because they say at the top the velocity is 0. But they're not supposed to say that. Okay, this one is from my algebra class, and you have to find that on your own. Okay, you need to come up with the final velocity is 0, right? So it's what do we want? How high? So it goes up and then it goes down. Sometimes I forget to put the x-y axis, but you can do it for me. So this is y. You start here, initial position is 0. Sometimes I forget, right? Initial velocity here is 5. Acceleration is minus 10. And at the top, the velocity is 0. So the final velocity is 0, 1, 2, 3. Okay, so remember your kinematic equation, there is no time. You can divide the motion. You can take the whole motion here, or you can take part of the motion. You are the one to decide where you start your stopwatch. So you can start here, and then you can stop here. Or you can stop there. It's up to you, okay? You decide. So I'm gonna start here, and I stop there. So I'm gonna use the equation V final square equals initial, I put a 0 square, plus 2 times minus 10 delta y. Okay? So the final is 0, initial is 5, so 5 square is 25, minus 20 delta y. Okay, so delta y equals 25 over 20. So these are easy, right? Mm-hmm. Okay, so 5 over 4, which is 1.25. Okay, so positive, because the displacement is positive. Okay, and I want to bring your attention to one equation that we always forget is this one. The final velocity equals initial velocity plus 80. Do you agree? This equation here. So if you use that equation, sometimes you end up with a quadratic equation. which is sometimes annoying to solve, unless if you have a TI, there is no problem. But otherwise, you can do it in 2 steps, and usually you use that equation here. Okay, so for example, from A to B, the final velocity, let's say I want to find the time it takes to reach the maximum. So the final is 0, initial is 5 minus 10t. So the time it takes to reach the top will be 1/2, so 0.5 seconds. And then you ask your guts took physics. If it takes 0.5 to go up, how long does it take to go down? Yes, so 0.5. So the time for flight will be, so 0.5 to go up, 0.5 to go down. 1 second, very good. So if you remember these equations here, sometimes it can be useful to use that one. Okay, are you with me? You can bring a coffee. So you could have said also, I decide to stop my stopwatch, right? Instead of stopping it here, I'm going to stop it here. Okay, so I'm stop my stopwatch here. So in that case, from here to there, you go back. It's coming back to your hand. So what is the displacement from A to B? 0, very good. So the displacement is 0. Okay. Acceleration is still minus 10. Initial velocity is still 5. So let's see what's going to happen if I use the kinematic equation. So I can do delta y, okay, equals initial velocity is 5t minus 5t squared. Do you agree? So between, your motion is always between when you start your stopwatch and when you stop it. Okay, it's up to you. So the displacement is 0. So this is going to be 0 equals 5t minus 5t squared. So t equals 1. Okay, so it's a different way to do it, just to make sure. Another solution, if it's a math class, you will say t equals 0. Duh, you know, it doesn't really help, of course. And if it's in your hand that t equals 0, the displacement is 0, right? So we want only that solution here. Okay? Is the acceleration changing during free fall when you are tossing or dropping something or getting mad? Acceleration? Never. It's always negative 10. Tossing, free fall, right? Dropping or just getting mad. Always negative 10. So here, ask your guts. It makes sense. You have 2 situations. Okay, situation 1, you toss and you have an initial velocity of 30. So it goes up and then it goes down. Second situation, you fall, you mad. It's a mad situation. Like this, initial velocity is negative 30. Will they hit the ground with the same speed? Yes or no? Obviously, this one will take more time. But is the speed will be the same? Remember, here we have a symmetry, right? It's going to be 30, 20, 10, 0, and then minus 10, minus 20, and then minus 30. So will they hit the ground with the same speed? Okay, so if you take this situation, it goes 20, 10, 0, minus 10, minus 20, and here it's going to be 30 again. So if you start your stopwatch here and you finish there, and you compare to here, you start your stopwatch here and you finish there. Don't we have the same situation? Yes. So will they reach the ground at the same not at the same time but with the same final velocity? Yes, because they both experience an acceleration of 10 down. So it's going to increase 30, 40, 50, 30, 40, 50. Which one will take more time in the air? Yes, the first one, because it goes high to the dark side and then come back. But the final velocity will be the same. Because we have a nice symmetry. Okay, so you can see the symmetry here. If you neglect a resistance, it takes as much time to go up that it takes to go down. And when they are at the same location here, the same magnitude of the velocity, of course, not the same velocity. Yes? Yes.
Yes, correct. Should it be the acceleration negative 10 or just 10? Or that's
Okay, okay, so the notation, so when you do it this way, the direction is given by the head, by the arrow. So yes, this is A equals negative 10. But if you're using an arrow, you will say A equals 10. So that will be, I should put like G. You're right. I should put G. That will be the magnitude. But then I see that it's pointing down. It's a good question. So likewise, if you have a velocity pointing to the left here, so you will put only the magnitude, something like that, but you know that it should be negative 4. Okay? So it's a good question. We did that. Okay, so these problems are easy. These problems are easy, and you have the solutions, by the way, in my Dropbox. I want to do this one. That's from your book. That's why I wanted you to get the same book, but if you have another book, it's fine. By the way, someone asked me, you have several university physics. It's not the same author, but they call it university physics because it's the physics that you learn in at the university. It's not very creative, but that's so. Okay, let's try to do this one. Talk to each other, help each other. I don't want to take too much time. You're gonna have homework, right? So for the homework, make sure you take it seriously, that you don't look at the solution. It's easy to find a solution. Anyway, you have tutorials. And very sadly, you have ChatGPT, which is very annoying. Or whatever AI. But it's not going to serve you, right? You want to find a solution on your own. On your own. Because then you have other classes to take. Okay, so first we want to make a drawing. Let's do a drawing, okay? Let's do your drawing. No, don't look at me. So you always have a door here. And hopefully you have window. Hey, good morning. Okay, so you make your drawing. So this is the roof railing. This is you. Okay, initial velocity is 15. So I'm going to put a 15 just for the magnitude. the ball is then in free fall, okay? So it's gonna go up, boom, 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 and it's gonna go down, boom, boom, boom. Okay. It misses the railing, okay? Find the velocity and the position. Okay, so do it. The more you do it, less it will be easier. So I'm gonna take my x, y here. So that way I can say that the initial position equals 0 when I start my stopwatch. And I'm going to decide also that up is plus and minus is down. Okay, so help each other. Okay. So A. Yes, do it. 1 second. So 1 second. So the position. So the displacement. You always find the position and then you look at your initial position. So displacement. Okay, so you know your equation by heart. It's going to be, they don't give the height, right? So initial velocity, 5t minus 5t squared. So that's going to be equals to, are you doing it? So 15, so at t equals 1, right? So 15 minus 5, which is 10. Very good. And then the velocity, so velocity, okay, it's going to be the initial velocity and it's going to increase every second by 10. So that's going to be 5. So it means it's positive. So that means at t equals 1, so you start to your stopwatch here, t equals 0. At t equals 1, I'm still going up. That's what it means. I'm still going up. And if I look at the position on the number line, I am at 10 meters. So I'm somewhere there. Do you agree? Are you all doing it? More you do it now, it makes the time go faster. So t equals 4 now. So delta y equals 15t. So 15 times 4 minus 5 t squared. And you get, so the book will say 9.8. Why? I don't want to make my life complicated. So 10 is easier, right? So it's going to be 15 times 5, no, 15 times 4 minus 5 times 16. And you get the equation, the kinematic equation. Yes. So what do you get? Negative 20. It's the first equation. Delta y equals V0t plus AT, but it's free fall. So this one is negative 10. Initial velocity is 15. So negative 20. And what's the velocity? Negative 25. So what's happening? We are on the way down. So here, obviously, it's going to be 15, okay, because everything is symmetric. And then I am somewhere negative 20 somewhere here. And that will be negative 25. Okay, it's easy. Negative 25. No, negative 20. Do you agree? So again, we are using the first equations of kinematics. We replace A by minus 10 because free fall, it will be always negative 10. And we are replacing X by Y because you are going up and down instead of right and left. Agree? And you say, yes, we agree. Okay, the ball velocity when it is 5 meters above the railing. So we want the velocity when it's 5 meters above. So you're going to translate that as displacement is 5 meters. Yes? Yes or no? Yes. And what do we want? We want the velocity. Yes. Because t equals 4, so you do 15 minus 40. Right? You need to have like on your tablet or notebook or next to you the equation of kinematics always. So that way you don't need to memorize. So delta y equals 5. What is the velocity? So you see the time is not given. So which equation you're going to use? The what? So delta y is 5. Well, we can find the time. I don't want to find the time. I want to take a shortcut and use the equation without time.
I want to use the fourth.
The fourth equation. Oh, the fourth equation. So remember, don't forget your kinematic equation, right? So this one has time, this one has time. This one,
Oh,
I mean, so this one does not, okay, this one, it's not the shuffle, but it's the same equation, right? This one does not have time. It's a very useful equation. It has to do with conservation of energy. It says that the work done by gravity will change the kinetic energy. That's what it says. Okay, don't forget everything you learn from one day to another day, right? You need to study in between. That will help. So V final square equals initial square minus 20 delta y. Why is it negative 20? Because it's a equals negative 10. 2 times negative 10 is negative 20. So final velocity equals initial, which is 15 square minus 20 times displacement is 5. And we have to be very careful with the sign. Okay, 15 square minus 100, 120, and you take the square root. Yes, 11 something, right? Let's say 11. Just 11 or plus or minus 11? Good. So why do we have two solutions? Let's find out if it makes sense. So when it's 5 meters above, so we are here, right? That will be 5 meters above. And that will be 11s, not 1. Okay, so you have two solutions. When it's 5 meters above the railing, right? Yes.
So we haven't started to fall back down. We only should take the positive.
We don't know. Do they say that?
Wait, 5 meters above.
So we don't know. So we don't know if it is, yes, maybe. So if it's
5 meters above the railing when you're coming up, 5 meters above the railing when you're coming down too.
exactly. So it depends if it's multiple choices. So both solutions will be good, right? You can be 11 or minus 11 because everything is symmetric. Agree? So look at the solutions, right? Plus or minus. Sometimes it doesn't make sense if it's time. Unfortunately, you can go back in time. Very sadly. But maybe one day. Any question? We good? Because this one is not hard. Again, if you have the textbook, you have the solution. And if you have the textbook in your backpack, inside your canvas, you have even a video without the French accent. So that might be good. What is the acceleration at the top? -10. Very good. Always -10. The velocity equals 0, but the acceleration is -10. Typical question, easy to trick students. It's always -10. That's right. Any question? Okay, so this one is really not hard, and it's from your book. Okay, so if you go, so I took picture. I'm not supposed to, maybe, but you see, it's from the book, and they make a drawing here, and they discuss. So if it says at what time has the ball fallen 5 meters below the roof railing? So what's that physical quantity? 5 meters below. Displacement. But is the displacement positive or negative? Negative. Okay. So that will be the type of question where you're gonna end up with a quadratic equation. And if you don't know how to use your TI, instead, you can do it in 2 steps. You can first find the final velocity and then find how long it takes. Okay, so first of all, can you just lay out the equations? Just lay out the equations, right? So the question here is the time elapsed, and you know, so in that case, you know the displacement is -5. Okay, so now we are, I don't know, I lost my picture here. We are -5. We are below the railing. We are somewhere here, right? -5. We are here. -5. Okay, so can you do it? So first of all, you put everything we know. Delta y is -5, check. Acceleration is always -10, check. Initial velocity is 15, up, check. 1, 2, 3, I'm good to go. And then naively, and okay, and the time. So naively, I say, okay, I'm going to use this one. Minus 5t squared. So displacement is -5 equals 15t minus 5t squared. Is that right? Do you all agree? Hmm? What? Yeah. No, but it's a quadratic equation. I can have a negative displacement. I cannot have a negative time. So if you find a negative time, you eliminate. So my quadratic equation will be -5t squared, or usually we like mathematician, I mean, math professor will like 5t squared, like a positive here, -15t minus 5 equals 0. Do you agree? So if you do it with your TI, can I send you a video how to do it? You should know how to do it just for engineering class. You should find t equals 3.3 seconds. Okay, so that will be the solution. Now, if you don't want, let me show you the trick. If you don't want to use quadratic equation, you can do it in 2 steps. You can use the equation instead. Final velocity equals initial velocity minus 20 times -5. Okay, and you find the final velocity equals to -18 because you are below, velocity has to be negative. So you do that first step, and then second step, you're going to use the equation. The final velocity, which we have, equals initial minus 10t. Okay, so if you do it in two steps, you're still going to find t equals 3.3 seconds. So I'm just giving you a trick. If you don't know how to deal with quadratic equation, then you can do it in two steps. But you have to be careful that we are below the railing. So the velocity has to be negative because it's on its way to the ground. Is that clear? You got that? Okay, so here you're going to have two solutions, plus and minus, but only the minus makes sense because you are below the railing. The ball missed the railing. And you will find the same thing. If you have a graphing calculator, you can make a graph and you find the root. Okay, in calculus, it's very useful to know how to use the TI. You can take derivative, you can find roots, you can solve matrices. So you should know how to do it. Okay, no question? So remember that equation, this one can be useful. And then from your book, so this one I'm not going to do it because then people is going to be lost if you have not taken calculus yet that you should have taken. But it's just if you have an acceleration, is the acceleration constant in that case? No. So can I use the kinematic equation that we know? No. Kinematic equation is only true when the acceleration is a constant. This one is a linear function of time. So then we have to use calculus. So if we want to find the velocity using the acceleration, what do? We integrate. Very good. We integrate. So we have to integrate. And when we integrate, we're going to find delta V. Final minus initial. Okay, so that's why the final V will be the initial, and then you have to integrate. If you integrate 2, you're going to get 2t. If you integrate this part, it will be 1/2. Agree? So it's a very nice way to use integral to practice. And then if you want to find x, the position on the number line, you will have to do delta x equals 2. And you integrate the velocity as a function of time. That will be the initial position, and you get something like this. It's a cubic function. Okay, if you lost, you use something like Wolfram Alpha, and they will break down everything into steps, or any app. Okay. Okay, let's do number 10 here. Just very quick, because that's the baby problems. So it's in my Dropbox, okay? I don't want to take too much time. How high? Goes up, boom, 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 dun, 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 go back. So initial velocity is 20, acceleration is always negative 10. How high? So I can start my stopwatch here and finish there. Okay, so what's happening at the top? Because we have 1, 2, we are missing something. So what's so special at the top? Very good. The final velocity equals 0. You want to make sure to have 1, 2, 3. How high means the displacement, right? So we can make a initial position is 0. Okay, so we can say between here and there, final velocity equals initial velocity minus 20 delta y. 0 equals 20 square minus 20 delta y. So delta y equals
20. Delta y is 20.
20. Yes, is that right? Okay. And the time, to find the time it takes to reach here, you can use this one, the final equals initial minus 10t. Very useful equation that sometimes we forget to find the time. That's the secret to avoid quadratic equation. You can use this one. So final equals 0. Initial is 20 minus 10t. So t equals 2. Is that right? Did I did it wrong? T. So how long, what's the flight time? 2 seconds to go up, 2 seconds to go down. What's the flight height? Time?
4 seconds.
4 seconds, right? T flight equals 4 seconds. You see that on the way, it's going to be, after 1 second, it's going to be 10. 1 second is going to be 0. Another second is going to be minus 10. And here it's going to be minus 20. So it's symmetric. Everything is symmetric. Okay? So you can do that on your own. For example, it's you have to do the drawing and you have assignment and you have tutorials. You have to do some work on your own. Are we good? Okay, let's start projectile motion. Ready? It's going to be start easy. Usually projectile motion, that's the hardest part. Okay, I don't know why. Students find it very hard for some reason. That's when they drop physics. Hopefully not you. Okay, so these are the kinematic equations that will be only true if you have no acceleration or if you have a constant acceleration. So I want to take two special cases that we're going to use for projectile motion. First case, you're going to cruise along the x-axis, okay? And there is no acceleration. So if there is no acceleration, that means the final velocity equals the initial velocity equals any velocity and it's constant. That equation will be the displacement is your velocity that stays the same times time. Do you agree? It's a linear equation. Or you can say that the position on the number line equals the initial position plus Vt. So that's cruising on the number line. If I make a graph, x as a function of t, you get a line that will be your y-intercept, and the slope is v. If I want to look at the velocity as a function of time, it does not change. And acceleration is 0. Okay, so we're going to use these equations. Yes.
Yeah.
Final.
Wait, what about
That
VI equals VI?
Vi is the initial velocity equals v.
Any.
Constant.
Oh.
So Vi or V sub 0, you can just say V. Okay, now we take the case of free fall. So free fall, you have two situations. You drop, or you are mad, so you toss down, or you toss up. So free fall means now we are up or down. So positive, negative, that's a y-axis. Free fall means that we have an acceleration of -10 always. We're going to have a final velocity, initial velocity, right? Initial velocity, and up and down. And then what else do we have? We have a delta y. So we're going to use the equation v final equals initial minus 10t. So that will be for free fall. So constant acceleration. Okay, always -10, free fall. And then we have the equation delta y equals initial t minus 5t squared. And then we have the equation v final square equals initial square minus 20t. Okay, so for projectile motion, and you understand what a projectile motion, it's something that you throw in the air, but now we are in 2 dimensions. We're going to use two set of equations. We're going to use that set of equations for a cruising motion on the number line, and we're going to use the free fall equations at the same time. So I will explain more. Okay, so let's go to projectile motion, which is a motion in 2 dimensions. So when you have a projectile motion like this, right? So if I take a piece of paper here, and we neglect air resistance. So if I do something like this, right, I have a launch velocity. It doesn't go right or left. It doesn't go up and down. It's doing two things at the same time. So it's going to move forward. And because there is no air resistance and no force, it's going to move forward at a constant velocity. But at the same time, it's going to go up and then it's going to go down. So it's going to doing two things at the same time, moving forward and going up and down. So you see, and what's that beautiful graph? Parabola. Okay, it's a quadratic equation. So example, you can be convinced by that. Hippie jump. I don't know if I say it right, but you see, if the skateboard is moving forward at a constant velocity, sure enough, you're gonna end up on your skateboard as long as it does not accelerate. So two things at the same time. You are moving forward at the same velocity as your skateboard, but you are also going up and down. If you look at the skateboard, relative to the skateboard, so if you put a little camera on GoPro on the skateboard, like looking, you're just going up and down. From the point of view of the skateboard, you're going up and down. From someone looking from the outside, you describe a parabola. Okay, so you're doing two things. You're moving forward at a constant velocity and you're going up and down. Agree? So that means we're going to end up with two sets of equations. One set for cruising along the horizontal and one set for going up and down. And it's Galileo that understood that those two motions, up and down and forward, are independent from each other. They just ignore each other. I'm moving forward, I'm going up and down. Do your business, I don't care. So you can divide motions into components. So let's see. Okay, you find treasures on X, right? So each time I see something cool, I download, but you can get the point. So don't do that. Do you see that? That make the good. Thank God that he didn't accelerate. Okay, if you accelerate, it can be very bad. So you are doing two things, up and down, and you are moving forward. So I don't know if you're gonna do it in lab, but there is this famous experiment as well. So it's moving forward at a constant velocity, and the ball is going up and down, and it's coming back. Same velocity. If it's accelerating, it doesn't work, right? So you can see that here. Oh, sorry.
Ball landed back in the cart. Why did it do this? Well, when the ball left the cart, it had the same horizontal velocity, v, as the cart. While it was in the air, everything acting on the ball was gravity. That was only acting in the vertical. Gravity was not affecting the horizontal speed of the ball whatsoever. So while the ball was in the air, its horizontal velocity didn't change, and therefore it landed back in the
So two set of equation. Now, if there is an acceleration,
here at top. This piece of string to the cart. And the string will be attached to this map, which will be hanging over this pulley at the end of the track. Now, the question is, when I release the cart, and the ball is along at the trigger, where will the ball land? Will it land?
what do you think? Behind, right? Very good. So all this understanding came with Galileo, right? He's the one who did that famous experiment. Um, Before that, it was not very clearly understood. So if someone drops something from this height, it's not going to fall behind. If the boat is moving at a constant speed, it will drop back in the boat. Okay, because from his frame of reference, it's describing half of a parabola, but from his frame of reference, it's just in free fall. So we are using two sets of equations. And then I have a last one, which I found very cool. That makes the point two. So it's just cool. But the point is, it's a situation of tossing. Even if something is tossed, right? So he's going up and down, but at the same time he's moving forward. So it's gonna be a parabola. Doesn't look very safe to me, but okay. So let's take right away an example. You can do that as a demo. You see, so the car is cruising along, so a constant velocity, and we're gonna say it's going at 10 meters per second. That's way too fast. It's just to make the computation easier. It's actually 10 miles per hour. And then someone is here and that person drop. So when you say drop, that means that the initial velocity down is 0. You don't get mad. You just drop. Okay? So it's doing two things at the same time. It's cruising along the x-axis, but at the same time, relative to this person, it's just in free fall, accelerating down. So given the numbers that you have, can you come up with the two set of equations? And the question is find delta x. So two set of equations. One because it's cruising along the x-axis, and one because it's falling down. So velocity, we say 10 meters per second, just to make our life easier. But 10 meters per second is too fast, right? We just pretend. So we're gonna do 2 meters per second. So I'm showing you the methodology, right? So you can make a table here, and you say that will be along the x-axis. So that will be forward, right, or backward or horizontal, and that will be the vertical. So that will be the y-axis. Okay, projectile motion, you always say here we're gonna have an initial velocity that will stay the same. Sometimes you know, sometimes you don't know. In that case, I know, so I'm going to put that here. So that will be your initial condition. And the kinematic equation that you always use for cruising is this one. And then on that side, you say, okay, it's a free fall. So I'm always writing down initial, the acceleration is -10, and then everything you know. And then I'm going to make a tunnel, like a little tunnel here, because the only thing they have in common is the time. Okay, so the time will be the same for both, obviously, right? It's not like we are getting in another universe and then all of a sudden you have two frames, one for the car, and they are both happening at the same time. So what do we know? What else? So we have 0.7. So is it up and down or left and right? Up and down, right? So I'm going to put that here. So delta y, is it positive or negative? Negative. So it depends where you take your frame of reference. So I'm going to take it here. So you have to decide, right? Plus, that will be y, plus that will be x, that will be origin 0. So here I'm going to say delta y equals minus 0.7. What else do we know? Can we say something here? You always try to know, you will always know. V? Very good. Do you all agree? Right? You don't get mad. Think of that. Are you getting mad? No. Just exactly. And now I have 1, 2, 3. I'm happy. So I want to find my delta x. Okay, let's see if I can find my delta x. Delta x equals 10t. Oh, I need time. So I'm going to go here and I'm going to solve for the time using, this is free fall, okay? So I forget about my forward motion. I am in the frame of reference of the guy, looks like a guy, inside the car. So inside the car, he's just dropping something and it will end up just at his, on the same axis, right? So I am in that frame of reference. So can you find the time? So I can use my kinematic equation. Delta y equals initial velocity minus 5t squared. So delta y is minus 0.7 equals 0 minus 5t squared. So t equals, and you take the square root, right? So you get so about 0.4 second, and exactly. So we take the positive one, and then there is a little. I don't know if you know quantum physics. Tunneling effect. Choo, 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 choo. No, I'm just kidding. You just go this. You can use the same time. So delta x equals 10 times 0.4. So delta x will be 4. Okay, so time is the only thing that can cross here. The time will be the same for both, obviously, but the equations will be totally independent. Exactly. Now you can do that. You can do this. There is a. You can do that. He has appropriately an apple. The apple that falls, and you see from his frame of reference, the apple is always under his hand. But from my frame of reference, I see that like half of a parabola, like just like this, right? Okay, so with the phone that we have today, and you can slow down, you can verify. Okay, so that's the big idea. Now we can make it more complicated. We can throw something in the air, and still we can decompose the motion into two sets of equations. One will be just up and down. Okay, so it's tossing up and down. One will be forward. Except that we will have to talk about vectors because we have to find components, but the same idea. So that's the big idea, and that was introduced um, by Galileo. Okay, so slide number 7. So I just want to show you, for example, here I have okay, you can see that. Maybe you will do that in the lab. You see what's happening here? I can slow down, speed slower. I'm coming back. So now it's going to be a situation where it's the same situation actually, right? So you have a situation where you have the ball here. It's moving at a constant velocity because there is no friction. And then here it has an initial horizontal velocity. Does it have a vertical velocity? So if you are located here, you're just gonna see that it's gonna fall, right? It's gonna fall, it's gonna be in free fall. Okay, so this is also projectile motion, but it's the easiest case, okay, when you have no vertical initial velocity. Okay, so you're going to have two sets of equation along the x, along the y. Here you do have an initial velocity, so you have delta x equals v0t, and for that one you have a equals minus 10, velocity initial equals 0, and then you have a displacement here, and you can use kinematic equation. Okay. Toum, 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 meow. Bon. I, there was an app, but for me it was easier this way. Playback, slower. Look, can you see? So what's happening along the forward motion? Is it moving at a constant velocity or is it spinning up? Constant velocity. So every second it's covering the same distance. The velocity here stays the same along the x-axis. But along the y, you see, it's in free fall. So the velocity is going to increase. Okay, you can see the velocity at the beginning here. The y, the velocity along the y is there any y here? No. And the velocity is going to increase, 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 increase. Okay, I have another app to show you. Reset. I want to have 0. I want to show you the velocity here. Okay. So what you see here, that will be the forward velocity, stays the same, and that will be the slow motion. Okay, that's better. Ready? Okay, look, 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 look. Do you see how this is going to increase, but this one does not change, right? See, the velocity along the y is increasing, increasing, it's in free fall, but the x component does not change. Now, if you want to look at the acceleration is always -10, but it's going to influence only the y-axis. It does not have any impact with the y-axis, x-axis, right? Position is just the position. Okay, so that's project. Okay, that's the idea. Okay, let's do this one. So it's an airplane, and the airplane is just dropping a package. So the package has the same velocity as the airplane. So from, if you want, you can think of it like that. From the frame of reference of the airplane, the package will be always underneath as long as it's moving at a constant velocity, so it's in free fall. From someone on the ground, it's going forward as well. So it's going to describe a parabola. So that's why you need physics, right? Otherwise, you're going to miss your target. Or you might kill someone there on the way. So you have the vertical displacement, you have the initial velocity along the x, and what do they want? The time. You want the time. So you help each other, talk to each other. Do your formalism, the formalism that I show you, do that. And then you do it step by step. And then you practice and practice and practice until it makes sense. So if I do the formalism, I'm going to do here forward motion y-axis, that will be free fall. So I'm going to take this like this, right? So that will be x and y. Okay, so what do I know? I know this is always negative 10. They are giving me the displacement, so delta y equals minus 1050. No one is getting mad. So you see it's just dropping. Okay, for the x-axis, I know that it's going to be 115, and then delta x is always 115t. Okay, and then you use your kinematic equation. So do it. So delta y, initial velocity, I don't know, so it's going to be minus 5t squared, which is negative 1050. Uh, is that right or no? Is it the vertical displacement? Yes, the vertical displacement is that. So t equals the square root of 1050 over 5, because it's the vertical displacement, so it's delta y. 14? Do you all agree? 14. Okay? And find the displacement delta x. So I'm gonna make a little secret door, a back door here. There's a little door here. It's secret. So delta x will be equals to 115 times 14. Which is 1000, right? Okay, so 1.6 kilometer. What's your name? Huh? Michael. Yes. 1600. Okay, meters. Do you all agree? Okay, let me try to trick you. What is the final velocity along the x-axis? Is is there an acceleration along the x-axis? So it's going to be the same. Yes? Because it's moving forward. Moving forward, it's cruising forward. Like the airplane. You see, the airplane is just here and the airplane is moving at the same velocity. What about the final velocity along the y? Exactly, you have an acceleration, right? So it will be minus 10 times 14. So final will be negative. Okay, so usually to tell them apart, we're going to put a little x here to say it's along the x, and a little y here to say it's along the y. So that's going to be called an x component, and that will be called a y component. Now we do that. That's a mathematical trick, right? It's to make our computation easier. But at the end, when you're gonna get the package here, it's not going to be x component and y component, right? You will have to find the final velocity here. So that will be your final velocity. It has two components. It's just that component here. It's an introduction to vectors. That component here is going to tell you how fast it's moving forward. This component here will have the information how fast it's going downward. So how fast it's gonna be when it's gonna reach the ground. So if you have ice, for example, if there is no friction, not only is gonna hit the ground, but it's gonna slide. Okay, if you have no friction, so it's doing two things at the same time. But that will be the velocity. So the final velocity here has two components. It has a forward component, 115, and a downward component, 140. So it's not on scale. I should do something like this. So using geometry, how could you find that velocity here? Pythagorean theorem. So if I want to find the final speed, which is a scalar, and don't worry, we will have to go over vectors. So for this weekend, if you can review in my Dropbox, you have a very nice video. So it's a YouTube channel that actually try to attract you to the website where you have to pay for tutorials. But that video was available, so it's in my Dropbox now. It's about vectors and how to find the components of vector. It's very nice, and it's a very nice YouTube channel as well. You can find, he's very good at teaching. So I say that you should go to Dropbox and look at those videos about vectors. And if you don't remember cosine, sine, and tangent, I'm not going to teach math. Okay, you need to go over cosine, sine, and tangent. Very simple trick. Question? So that will be for this one. So what do you think is going to happen? So along the y-axis, the same thing is going on, right? So if you drop something, or if you give it a horizontal velocity, the y-axis totally doesn't care about the x-axis, right? I'm doing my free fall thing, you do your forward motion, I don't care. We are not belong to the same world. So what do you think is going to happen? Do they hit the ground at the same time? Yes, yes, because they have the same vertical motion at the same time, and they will have the same final velocity. So I can show you that here. No, there is one that is, no, this one is funny. I still have, is that 1 minute? Yeah, I can do this one. It's not funny, but I found that it's very cool. So it's a demo. Where you're going to have two sides here. One side will launch horizontally a projectile, and the other side will just drop. So launch, horizontally drop. So here you're going to have a horizontal velocity to begin with. No, this one is the opposite. It just drop, and this one you have some horizontal. The one with the spring, you have a horizontal velocity. So horizontal velocity, drop, or the opposite. I don't know if it's gonna show again. So let's just watch it. Watch it last time. Isn't that cool? Right? Now you can do it yourself, but you need to have a good hand coordination.
Because I'm going to bring this bocce ball straight onto my side, while at the same time drop this bocce ball straight down. The question is, which ball hits the ground? The one that I throw off to my side, the one that I let drop straight down, or they both hit at the same time? As you can see, they both hit the ground at the same time. Well, how did this happen? Well, after I let both balls go, the only thing acting on them was gravity. Therefore, they both fell at the same rate. It didn't matter that I gave one ball some component of velocity in the horizontal direction. That's not affected by gravity whatsoever. Only motion in the vertical direction is affected by gravity. Therefore, I can throw the ball as hard as I wanted off to the side, and it would still hit the ground at the same time as the ball that I dropped straight.
So this is Virginia University, I think. So why